So continuing with the redox reaction, this is our lecture number 7. What is stoichiometry of redox reactions? How does it help in the calculations? Stoichiometry of the redox reactions is that it is the number of moles of the oxidant and number of mole of the reductant. They are combining in the redox reactions to give the complete redox reaction. If we know the number of moles of the oxidant as well as the reductant, then we derive a formula to make the stoichiometry calculations in the redox reactions. Let us see if N1 number of moles of reductant combined with N2 number of moles of oxidant and their molarities are known to us in the reaction or volumetric analysis. Then we derive a formula for stoichiometry calculations. Let us see 2KMnO4 combines with 10FeSO4 in the presence of H2SO4 concentrated to give you K2SO4 plus 2MnSO4 plus 5Fe2SO4 thrice and plus water. If we see sulfate here, 1, 3 and 5, 8. So we'll be having 8 sulfuric acid here. So this will be the balanced reaction here. So in this reaction what we see that 2 moles of KMnO4 N1, it is oxidant. So we have taken the number of moles of the oxidant, that is N2. This is N1. So we have the formula. If the molarity of KMnO4 is M2, V2, volume is V2, number of moles are M2, then it must be equal to molarity of ferrous sulfate multiplied by volume of ferrous sulfate upon its number of moles. So this is the formula. For stoichiometry calculation, now put their values here. We have 2 moles of the KMnO4, therefore we have M2 V2 upon 2, that will be equal to M1 V1 upon 10, or in other words we can say M1 V1 M2 upon 5, that is equal to M2 V2 upon 1. So this will be the formula used for making stoichiometric calculations during this reaction. Then we have a numerical problem based on this formula or this expression. What is that numerical problem? Let us see. So this is our question number 2 of this lecture. The problem is, how many grams of potassium dichromate are required K2Cr2O7 are required oxidation of 20 gram of ferrous sulfate to ferric sulfate in acidic medium. How many grams of potassium dichromate are required to oxidize 20 gram of ferrous ion to ferric sulfate in the acidic medium? Now let us see the balanced equation of this is first of all K2Cr2O7 reacts with sulfuric acid producing K2SO4 Cr2SO4 thrice plus H2O plus 5 nascent oxygen. Let us see the balancing of oxygen here. 3 sulfate, 4 sulfate, you can have 4 here. K2SO4, Cr2SO4, H2O, 4H2O, 5 oxygen. So we count 7 plus 23, 4 and 16, 23. This is 3 nascent oxygen. Now this nascent oxygen that is used by ferrous sulfate in the presence of acidic medium to give you Fe2SO4 thrice plus H2O. Multiply this equation by 3 to cancel out this oxygen. We have K2Cr2O7 plus 4H2SO4, 7H2SO4 plus 3, 6 FeSO4 and we get K2SO4, Cr2SO4 thrice plus Fe2SO4 thrice. It is 3 Fe2SO4 thrice plus 3 water and 4, 7 water. Now in this case, 1 mole of N1 here is K2Cr2, that is 1 mole. And ferrous sulfate are 6 moles. So now applying formula, your M2 B2 upon 6 that is equal to M1 B1 upon that is 1. Now in this case molarity of the solutions is not given, the weight is given and it is asked how much weight of oxidizing agent is required to oxidize 20 gram of ferrous sulfate. Now let us see, calculate the weights of these. This is 6 multiplied by ferrous sulfate weight, this will be 1 multiplied by K2Cr2O7 weight. Now ferrous sulfate weight, let us see, it is 152 multiplied by 6 and your K2Cr2O7 weight is 298 gram, 294 gram. This is 152 multiplied by 6. So now we are 6 into 152 grams of ferrous sulfate need K2Cr2O7, that is 294 gram. 1 gram will need 6 multiplied by 152 and 20 gram will need how much? So this is now stoichiometric calculations of the redox reaction. The answer will be 6.45 grams. So this is stoichiometry of the redox reaction. First of all, we have to arrive at the balanced redox reaction. After that, we will be calculating the number of moles of the reactant and product they are combining to give the products, and then we go for the numerical problem, what is asked and what has to be calculated. So this is the first topic and its related numericals on stoichiometry. Now we come to another topic, that is the applications of the redox reaction. Question number 3 of this lecture, what are the applications of redox reactions? Answer, it helps us to convert metal oxide into metals. It helps us in refining of some metals like aluminium, copper, zinc. So this is aluminothermy. Fe2O3 is reduced to iron in the furnace by using coke. Fe2O3 is reduced to iron by using coke. Aluminium oxide is prepared through aluminothermy. Number of biochemical reactions taking place in our body are redox reactions. Photosynthesis is a redox reaction where food is prepared by the plants. Six CO2 combines with 6 water in the presence of chlorophyll and sunlight to give you C6H12O6. This is glucose plus 6O2 plus heat plus energy rate ATP molecules they are generated. So photosynthesis is also a redox reaction where carbon dioxide is reduced to carbohydrates and water is oxidized to oxygen in the presence of chlorophyll and the sunlight. Then we have the oxidation of fuels is a important source of energy in vehicles, at home and in the body. In body, carbohydrates they are oxidized to carbon dioxide and water, and this is accompanied by release of energy which is used to carry out our cellular reactions. Then we have the electrochemical cells, electrochemical and electrolytic cells. Carry out number of redox reactions through which they establish conversion and relationship between electrical energy and chemical energy. So these are the applications of redox reaction. Then we have another important question. What is the difference between valency and oxidation number? Question number 4 is, what is the difference valency and oxidation number? So we'll be explaining this difference through columns. Valency, as we know, it is the combining capacity of the atom of an element or the number of hydrogens or chlorine or double the number of oxygen atoms with which combine with atom of an element. For example, lithium combines with one hydrogen, valency is 1. It combines with one chlorine, valency is 1. It combines two lithium combined with one oxygen, valency is again established 1 here. Now we have the oxidation number. It is the charge which an atom appears to have when it forms compound. For example, NaH, hydrogen appears to have -1 charge, it is having +1 charge. In H2SO4, sulfur is +6. So this is the residual charge left on an atom when all the other atoms removed from it, from the molecule in the ionic form. Then valency is only a number. It is neither positive nor negative. It is only a number. Nor positive or negative. It may be positive as we shown above, or negative. Positive when it loses electron, atom loses electron. Negative when it gains electron. Then valency can never be 0. It may be 0 in the uncombined state. Or in homomolecules which are found between atoms of the same element. Then we have, in some cases, valency of the element is fixed in all the compounds. In some cases, it is fixed in all the compounds. एग्जाम्पल के तौर पे कार्बन इज +4 in CH4, -4 in CH4, CH-Cl3 it is -1, CH2Cl2 it is -2. So in this manner, valency that changes in the compounds, it may have same values in the compounds. So here it is CH4, it is your +4. Valency is 4, it is not plus or minus. In C2H6 it is 4, C3H8 4, and C2Cl6 it is 4. So carbon has fixed valencies in these compounds. Then we come to oxidation number. It is different in different compound. For example, in CH4 carbon is -4, and in CH3Cl it is -2, and in acetylene it is -1. It may be different in different compounds. Oxidation number -4 in CH4, minus 2 in CH3Cl, minus 1 in CH2Cl2, minus 2 is chlorine here, it is plus 2. Let us calculate oxidation number of carbon. In this case that will be 0. In CH2. Then we have the next point. Valency is variable but limited to only two maximum values. Two values. It is neither 0. For example, valency of nitrogen is 5 in N2O5, and it is in NO2 it is plus 4. Similarly, oxidation number is also variable. Oxidation number is either too large, it may be different in different compounds of an element. For example, nitrogen form 5 types of oxides. In all those compounds, nitrogen has different valencies. In NO2, it is in plus 2 state, plus 4 state. In N2O3, it is present in plus 3 state. N2O4, it is in plus 4 state. N2O5, it is in plus 5 state. So this is regarding the difference between valency and your oxidation number. Then we come to another question. What are the different types of redox reactions? There are many types. Number 1, combination redox reactions. Here two compounds or two atoms, they combine together to give the product. These are called as combination reactions. C combines with O2 to give you CO2. H2 combines with O2 to give you 2H2O. So these reactions, they are called as combination reactions. Then we have decomposition reactions. But all the decomposition reactions, they may not be the redox reaction here. In these reactions, the compound is either of its own or decomposes by heating, and in the different compound produced through decomposition, the different atom, they have the different oxidation numbers, or they might be present in the elemental state also. For example, 2NaH, sodium hydrohydride, when heated, it changes to 2Na plus H2. So here oxidation number is 0, here 0, here it was plus 1 and minus 1. So in decomposition reactions, the oxidation number of the elements which were initially present in the oxidized or reduced form, they are reduced to their elemental state during the decomposition reaction. Similarly, in the decomposition of H2H2O by electrolysis, converts it into 2H2 and O2. Again, oxidation number are 0. Here it was plus 1, it was minus 2. So in these are the decomposition reaction where oxidation number is reduced to 0. 2KClO3 breaks up to give on heating 2KCl plus 3O2. And in some decomposition reactions, the change of oxidation number might not be observed. Here magnesium is plus 2, here it is again plus 2, and carbon is plus 4 here, it is also present in plus 4 here. So oxidation number might not be changed in all the decomposition reactions. Then we have third type of reactions. These are called as displacement reaction. Displacement redox reactions. Here one metal can displace another metal. For example, when FeSO4 combined with zinc, zinc can displace iron due to negative reduction potential of zinc is less than that of iron. You will get ZnSO4 plus Fe. Similarly, CuSO4 can also combine with zinc to produce ZnSO4 plus copper. So these are called the displacement reaction, where one metal is displacing another metal in these reactions. Then we have non-metal displacement reactions, where a non-metal displaces another non-metal. Displacement of metal. Then we have displacement of non-metal. 2Na plus 2H2O combines to give you 2NaOH plus H2. Similarly, 2K plus 2H2O combine to give you 2KOH plus hydrogen gas. So these are the non-metal displacement reactions. These are the metal displacement reactions. These are non-metal displacement reactions. So displacement reactions, they are of two types: metal displacement and non-metal displacement reaction. Then we have the disproportionation reactions. So disproportionation reactions, in these reactions an element in a particular oxidation state is simultaneously oxidized or reduced. So in these reactions, the oxidation number of an element increase in one compound, it will decrease in another compound. So such reactions, they are called as disproportionation reactions. Let us see one reaction. 2H2O2 decomposes to give you 2H2O plus O2. Here oxidation number of oxygen was -2, and in this case it is changing to +0, and in 0 in this case. And let us see now what is the oxidation number. In H2O it is -2. In H2O2 it was -1. So oxidation number has changed in this case. In this case it has increased, here it has decreased. These reactions are disproportionation reaction, where a compound is splitting into two compounds. In one of the compound its oxidation number has increased, in another compound its oxidation number has decreased. Similarly, P4 combines with 3OH. So P4 when combines with 3OH, it will be producing 3H2O liquid, PH3 plus 3H2PO2. It produces PH3 plus H2PO2. So in this reaction, oxidation number of phosphorus was 0 here. Here it is present in +3 state. In this case -4 and +2 is subtracted. It is in +2 state. So in one of the compound, its oxidation number has increased from 0 to +2, and in other compound it has decreased from 0 to -3. So this is a disproportionation reaction of phosphorus. Then we have the next reaction, that is O2 combines with Cl2 combines with OH negative. So Cl2 combines with OH negative to give you ClO plus Cl plus water. Now in this case, chlorine was initially in the 0 oxidation state. Here it is present in the +1 state. Here it is in the minus state. So in one of the compound, its oxidation number has increased from 0 to +1. In another compound, it has decreased to -1. Then discuss the redox reactions as the basis of titration. So we can say the volumetric titrations which are performed in the lab, they are based upon the redox reactions, and we have already studied some of the redox reactions in the volumetric analysis. We have studied the reaction of KMnO4 with the ferrous sulfate and oxalic acid, where KMnO4 act as a oxidizing agent, while ferrous sulfate or oxalic acid they act as a reducing agent. Similarly, we have seen the reaction of potassium dichromate with ferrous sulfate or oxalic acid in the acidic medium. So, first of all, we are doing with the potassium dichromate titration. So, this question is discuss some of the redox reactions in volumetric analysis. First of all, we have KMnO4 titrations. In these titrations, they are carried on the acidic medium. We are using the solution of reducing agent in the titration flask, and we add sulfuric acid to it to perform the titration, and then we add KMnO4 from the burette to these solutions to carry out the reaction. Let us first see the oxidation of oxalic acid by KMnO4. Action on oxalic acid. So we have 2 KMnO4 plus H2SO4 plus C2H2O4. This is oxalic acid. They combine to give you K2SO4, 2MnSO4, H2O plus carbon dioxide. Now we balance this equation. 2 KMnO4 combines with the 8 H2SO4 molecules here, and we take oxalic acid as your 5 molecules here. We will be getting 10 carbon dioxide from here. We get K2SO4 1 mole, 2 MnSO4. This is MnSO4, and we get 8 water molecules in this case and 10 CO2. This is our redox reaction, balanced redox reaction. Then we study the action on ferrous sulfate. So 2 KMnO4 again combines with ferrous sulfate in the presence of H2SO4 to give you K2SO4, 2 MnSO4 plus Fe2SO4 thrice, and we get water molecule in this case. So this is another redox reaction with ferrous sulfate. Here 10 molecules of ferrous sulfate. They are needed to react with 2 molecules of KMnO4, 8 molecules of sulfuric acid. We will be getting 8 water here, and we get 5 Fe2SO4 thrice, K2SO4, 2 MnSO4 is again 2 molecules of it. They are formed from this. Then we have potassium dichromate titrations. Second is potassium dichromate titration. Here K2Cr2O7 combines with concentrated sulfuric acid and ferrous sulfate. 7 ferrous sulfate here. We will be getting K2SO4 plus 2 MnSO4. Cr2SO4. Plus Fe2SO4 thrice plus water here. Now in this reaction, K2Cr2O7 combines with 7 H2SO4 plus 6 FeSO4. It will give you K2SO4, Cr2SO4 thrice, 3 Fe2SO4 thrice, and along with that you will be getting water molecules. So water molecules, 7 water molecules will be formed in this reaction. So these are your volumetric analytic titrations which involve the redox reactions. So this is all about our redox reactions unit. Tomorrow we'll start with the fresh unit, that is inorganic chemistry. Chapter will be hydrogen. Thank you very much.